So now we're going to look at some of the patterns and features of the modulo 7 tables. And if we look at, first of all, the addition table, and we look at the main diagonal, that's the one going from the top left down to the bottom right, then we see that the table is symmetric about this. So we have 3 and 3, we have 4 and 4, and this just corresponds to the fact that A plus B is equal to B plus A. So for example, 2 plus 4 is equal to 6, and 4 plus 2 is also equal to 6. And a similar fact is true for the multiplication table. Next, notice that for addition, each one of these rows is in fact a cyclic permutation of the top row. And what I mean by that is to obtain this row from there, then you just move this row to the left by 1 and the 0 comes around to the end. So that's how we get this row here. And similarly for the other rows down below, and likewise for the columns. Each one of them is a cyclic permutation, or if you like, a cyclic rearrangement of the top row, or for that matter of the leftmost column. And this is something which is true for all modulo tables for addition. Finally, for the modulo 7 table, let's look at the multiplication table. Apart from this row of zeros and this column of zeros, each row here is a rearrangement in some way of the top row. So 3, 6, 2, 5, 1, 4, we have that each of the elements in here actually occurs in here exactly once. So here's 1, here's 2, here's 3, 4, 5, and 6. Another observation we make is that, and this will become more noticeable when we go to the modulo 8 tables for multiplication where it doesn't occur, that in particular, in every row we have a 1. The significance of that is that if I look at this row, for example, here is the 1, so that 3 times 5 is equal to 1. And in this row here, here is the 1, so 5 times 3 is equal to 1, as it should. 3 times 5 is equal to 5 times 3. So we can always get a multiplicative inverse in the case of the modulo 7 tables. We also normally omit the green row and the green column of zeros because no new interesting information is given in this case. And also, in this particular case here, we obviously cannot get a multiplicative inverse. There's no number which, when multiplied by 0, will give us 1. Whereas there certainly is a number which, when multiplied by 1, gives us 1, namely 1, which multiplied by 2 gives us 1, namely 4, and multiplied by 3 gives us 1, namely 5. Features that occurred here in the case of mod 7 essentially occur in all cases where we're taking multiplication modulo a prime.